Well, we're going to look over some applications of finding extrema functions of two variables over a given domain. And the problems really are similar to optimization problems you might have done in Calculus 1. In fact, sometimes we'll even use some Calculus 1 techniques for parts of the problems. So, let's start with this one. A flat circular plate has the shape of a circle of radius 1, center at the origin, so x squared plus y squared less than or equal to 1. And it's heated such that the temperature at a point xy is, T at xy is defined as x squared plus 2y squared minus x. So find the temperatures at the hottest and the coldest places on the plate. And I have a graph of it, so the plate itself should be above the circle, which the circle would be, here's the origin, here's the y equals 0, here's x equals 0, so the circle is pretty much what I have drawn here, only I didn't really draw the circle, but the circle is in the xy plane. And the graph is somewhat above the xy plane. We're trying to find, with this graph of temperature, where over the circle, I'll draw the circle again to show you where the circle is. The circle is right here. The circle, where over the circle is this temperature function highest, and also where in the entire circle is the temperature the lowest. So that's what we're after. We're trying to find that. So since we have our function of two variables, here it is, it's easy enough to differentiate with respect to x. We get, check it out, 2x minus 1. And differentiated with respect to y, we get positive 4y. So our two partial derivatives with respect to x, 2x minus 1, with respect to y, 4y. And so setting both of these partials equal to 0, we get a critical point at the point x is 1/2 and y is 0. Now, we'd like to look at that differentiating device that involves some second derivatives to determine if it's a maximum or a minimum or a saddle point, or hopefully we'll be able to tell from that. So that means we need a second derivative with respect to x, which would just be 2. The second derivative with respect to y would be 4. And the mixed partial, the derivative of this with respect to y is 0, the derivative of this with respect to x is 0, so the mixed partial gives us 0. So what we have is 2 times 4 minus 0 squared, so that's positive. And since our second partial with respect to x is also positive, because it's positive 2, so you recall, so this must be a minimum point at the point x equals 1/2, y equals 0. So good. We got a minimum point, but what remains is to check the border to see if two things. One is we could get a temperature even colder than that at the border, or, and I think it is the case, that that's where the warm temperatures exist, there on the border of this circle. On the border of the circle looks like somewhere over here, and maybe somewhere over here is where we have the high temperatures. So let's see if we can't pinpoint where that occurs. So on the border, we know that y squared equals 1 minus x squared, because after all, x squared plus y squared equals 1 is the equation of the circle. So we can examine the function f of x equals x squared plus 2 times, now that would have been y, but I replaced y with 1 minus x squared, and then minus x, which gives us negative x squared minus x plus 2. And if we solve this equation set to 0, we get x equals negative 2, which is not in the region, or else x equals 1. If x equals 1, then we're on the circle at the point where y equals 0, because if x equaled 1, see, then y squared is less than or equal to 0, so y has to be 0. Also, we know that solving this equation for x, the one x squared plus y squared equals 1, we get x equals plus or minus square root of 1 minus y squared. So we need to examine the one variable functions of y at the point where x equals 1, y equals 0. But let's see the one variable functions of y. Since x squared equals 1 minus y squared, so this is replacing x squared. This is part of the original equation, and then I'm going to say minus this, and this is the simplified version. Because this and this are like terms and they add up to positive 1y squared. And the other one is, of course, that was with the negative square root, this one's with the positive square root, so everything else was the same. So now we need to look at derivatives of this with respect to y. Set them equal to 0 and find a maximum or a minimum. And we're doing what we would have done in Calculus 1 now. So derivative of this, derivative 1, 0, derivative of this is 2y, the derivative of this, careful, since that's 1 plus y squared to the positive 1/2, then our derivative is going to be 1/2 times 1 plus y squared to the negative 1/2 times the derivative of the inside function, which is negative 2, and the 2 and the half cancel out, so we get y over square root of 1 minus y squared. Similarly, for the derivative of this part, we get 2y minus y over the square root of 1 minus y squared. And now setting each of these derivatives equal to 0, for this one, we could subtract 2y from both sides. Then I guess what we would do then is maybe multiply by this and divide by negative 2y, in which case we get square root of 1 minus y squared equals negative 1/2. And if you were to follow on this side, you get the square root of 1 minus y squared equals positive 1/2. So squaring both sides, we get y squared equals 3/4, or y equals plus or minus 3 square roots of 2. And we get the same thing with the other branch. So to find the x, then x would be the square root of 1 minus y squared. So if you check out what that is, this is 3/4 when you square it. So it's square root of 1 minus 3/4, which is square root of 1/4, which is 1/2. And ditto, we could get the negative version with x equals negative 1/2. And it wouldn't matter if we use positive or negative square root of 3 there. So we gotten the same result if we used negative square root of 3 over 2 here and here. So what's the story? Well, we know we have a minimum at minimum temperature at x equals 1/2, y equals 0, and if you check out the values for that, if x equals 1/2, then this is 1/4 minus 1/2, which is negative 1/4, and this is 0. So we get negative 2.25, negative 1/4. And at 1, 0, we get a temperature of 0. X is 1, y is 0. We got 1 minus 1, and that's 0. So yeah, we get a temperature of 0. At x equals 1, x equals 1/2, y equals the square root of 3 over 2. If, I keep running back to here, maybe what I should do is just go up here and copy this, so I don't have to run back so far to check. Got a little ahead of Max. Yeah, there we go. So now if x equals 1/2, then that's 1/4. That's 2 times 3/4, which is 3/2. So we got 1/4 plus 3/2 minus 1/2. So 1/4 plus 1. Right? So we get 1.25, and similar fashion for this one you get 1.25. If t is negative a half, what changes, this is still 1/4, but now this is going to become plus a half. And y, given at square root of 3/2, when you square it, you still get 3/4, so 2 times 3/4 is 3 halves, so we got 1/4 plus 3 halves, call it 6/4, so that's 7/4, and then minus x, which is negative a half, so that winds up being plus another half. So we had, oh golly, what do I have? I had 7/4 plus another 2/4 makes it 9/4, or 2.25. Similarly, this one comes out 2.25, and this one comes out 1.25, and we know from that the maximum temperature of 2.25 occurs at two different places, here and here. Notice x equals negative a half, and y equals square root of 3/2, or else negative square root of 3/2. And the minimum temperature of negative 1/4 of a degree occurs at the point where x is a half and y is 0. So look at the graph to identify these points. X is a half, y is square root of 3/2, that's about 0.86, so about here somewhere. Similarly here, but that's not a maximum or a minimum, but we do get a maximum at x equals negative a half, y equals plus or minus square root of 3/2, so as you can see, that's right about here or right about here. That'll be on the edge of the circle, and a minimum point occurs at x equals negative a half, y is 0, so kind of what we expected. And here is a picture. These two purple dots are showing the maximum temperature, and this purple dot here shows where the minimum temperature occurs.